Well, thank you very much for that really nice introduction. So it's very much a pleasure to be here. I haven't been to the Institute in a while, so it's really nice to be back. I am in the middle of a nasty cold right now, so I'm completely drugged up so that I can hopefully speak. So if I run out of here in the middle of the talk for any reason, it's because I'm sick, not because I don't want to be here. But just to be advised, and hopefully my voice lasts for the talk. So what I'm going to be talking about is basically a variety of physics that you can use millisecond pulsars for. I think that we're in an excellent time for millisecond pulsars. And the main reason for that is because of Moore's law. Moore's law has allowed us to make measurements in the radio for these very, very faint and difficult to measure objects that we weren't able to make 10 or 20 years ago. And it's kind of opened up this field, I think, tremendously. And one of the main bits that I'm going to talk about is NanoGrav and the direct search for gravitational waves using an array of millisecond pulsars in the sky. But I'm also going to talk about some of the secondary science, as I like to say, that comes from doing these searches. Because if we have to time the pulsars very, very well to detect gravitational waves, we get a whole bunch of other physics out of it for free. We measure neutron star masses. We do various different tests of general relativity. We find interesting systems that have great astrophysics in them. And so hopefully you'll see that I think we have a great chance of doing some fantastic physics, like directly detecting gravitational waves, and getting a bunch of other great stuff out of this long-term timing project with these pulsars. So this audience should know this, but since mostly you're a bunch of theorists, I will explain what these objects are in the way that we see them as observers, basically. So these are millisecond pulsars I'm specifically talking about. These are the ones that have much smaller magnetic fields by about a factor of 10 to the 4 than young crab-like pulsars. And that's those much smaller magnetic fields that allow them to spin very, very stably with time. And truthfully, we didn't know how stably they spun until just recently. Basically, these gravitational wave projects have shown us that these really, really are truly excellent clocks. We really did not know that until just recently. Standard neutron stars, you guys know all about that stuff. The one thing that is important to remember, especially for this audience, is that these are very faint objects. So even though they have tremendous luminosities and we can see some of them across the galaxy, the vast majority of these are local objects. These are within 1 or 2 kiloparsecs. We're only seeing the ones that are close by. And we need the biggest radio telescopes on Earth in order to see them, because the radio emission is incredibly low luminosity. So we really do need the biggest and best radio telescopes, and you'll see that's a theme throughout my talk. I'll be harping about radio telescopes. So where do these things come from? So you have the supernova produces a neutron star, and that neutron star is going to live for 10 or 100 million years, roughly, as a young pulsar. And then it'll turn into a 1-second pulsar and eventually die because it's spinning too slowly. But if there's a companion star, a red dwarf type star, much like our sun, a main sequence star, after stellar evolutionary timescales, say after gigayears, that star is going to evolve off the main sequence, and you'll get an accretion disk. You'll get a mass transfer. That ionized accreting material buries that magnetic field by about a factor of 10 to the 4 and transfers angular momentum, spinning up that neutron star. When the binary and stellar evolution ends, what you're left with is basically this. This is the canonical millisecond pulsar. You have a rapidly spinning millisecond pulsar in a perfectly circular orbit with a white dwarf. So this is the typical system. And it's perfectly circular because that X-ray binary phase is very messy, and so tidal dissipation circularizes those orbits. But this is what most of our pulsar systems look like. So most of them are in binaries. Only about 15% are isolated. And the way we get all the science from these systems is via pulsar timing. And this is the tricky bit. This is I mean, it's very conceptually simple, but it's a very different type of astronomical observation. So I'll talk a little bit about how this is done, because this is the crucial bit of how we can get such precision out of our measurements. And it's that sentence that's the key. We unambiguously account for every single rotation of the neutron star over time periods of years. So it's a pulse counting effect, and it's a very, very precise pulse phase measurement. And as you well know, if you do anything with phases, it's way better than doing it with periods or frequencies, because you can make phase measurements much more precisely. So this is an example time series with a bunch of pulses. This is dramatically expanded in amplitude. We never see individual pulses from millisecond pulsars. Normally, we have to integrate up tens or hundreds of thousands of pulses at least to be able to make a detection, even for our brightest millisecond pulsars. So this is just for just to give an example as to what we do. But in general, we make a measurement of the local spin period of the pulsar. And then in order to gain signal to noise, we fold the data modulo the pulse period. So we basically break it up, chop it into little bits, and then add those pulses one on top of each other to increase the signal to noise ratio. And when we do that, when we fold the data modulo, basically we're wrapping the data helically on top of itself. So time is actually flowing this direction, and the pulses are stacked on top of each other. And this is pulse phase, but pulse phase is also just another time measurement. But this is pulse phase versus time. And if you stack all the pulses correctly, then you get this nice line of pulses. And so our measurements at a day at the telescope are of averaged pulses. We'll measure when this pulse arrives as a function of time, and then we'll maybe make dozens of these measurements during a single day at the telescope. But it's many, many hundreds of thousands of pulses that are averaged together for each of those average arrival time measurements. And that's what we call these. We call these arrival times, or times of arrival. And with those times of arrival, and your eye's already done it. You've already made a line. You've made a timing model with your mind, which is the timing model is you see how the pulse phase changes with time. It's constant. And we can make a prediction then of when I come back to the telescope tomorrow where those pulses are going to arrive tomorrow. So I don't need to be observing in this intervening time, because as long as my model predicts the pulse phases linearly like this, I can extrapolate that to the next day, and I know exactly how many pulses I missed when I wasn't there. And it's really that simple. Once you have a model that can predict pulse phase quite well, you don't have to be at the telescope. You can go away, go on vacation, do other things, come back, and when you make a new measurement, it's right where you predict it. So that's what we have. We have a prediction that extrapolates forward in time. We make a measurement at the observatory, and then we check, like this third observation, to see if we're close. And in this case, we might have extrapolated slightly too far. Maybe we waited a couple days too long. But you can see that if you make this model, the pulse phase model, it's got a slight drift to it, so we're a little bit off there. But that's great, because that gives us, that's informative. That lets us update our model parameters. It improves our timing precision. And now we can make a better extrapolation for the next time we go to the telescope. And this is exactly how it works. We bootstrap up to a better and better timing solution. And we make then our observations and our predictions, and we subtract the two, and that's timing residuals. And so basically these measurements of the dark gray here compared to our model are timing residuals. That's what you see Pulsar people plot. These are our arrival times plotted in a residual format. So every day at the telescope is a little group of data points like this. And you can see here that as long as your timing model is good, you get all your residuals are near 0. This is in terms of microseconds, and this is about 2 years of data. These are a day of it at the telescope. And so like I said, each day at the telescope, there might be dozens of observations. And then there's times where we don't have any data, and times where we have intense amounts of data. This is an excellent pulsar right here. This was from the discovery paper of one of the best millisecond pulsars we know of right now. And if you just look at the discovery data, which is not ridiculously high precision, if you take and make a histogram of all these measurements to look at how we're doing, it's a Gaussian with about a 200 nanosecond full width of half max. So any of the many billions of rotations of the pulsar here, I can tell you when each rotation arrives to within about 200 nanoseconds, plus or minus. And when you do that, and if you think about all the things we have to account for to make that happen, the Earth's going around the sun, for instance, as you guys, I think, know. And even when that happens, there's tens of thousands of pulses just due to light travel time that you have to account for as the Earth's going around the sun. And it's got an orbit as well, so we have to account for the orbital parameters perfectly. All these things go into our timing model. So when we actually publish a timing model, it looks kind of like this. These are all the different things that we have to account for. These are the measurements. This is this little parenthesis there. That's the error The little parenthesis, that's the error in the last digit. So this basically means plus or minus 6 on the 1 there. But you can see the spin period, you know, there's 13, 14 significant figures. There's 12 or so significant figures in orbital period. There's, for position, proper motion, parallax, many significant figures. You get the idea. If you do this correctly, so you count each pulse, this stuff just falls out. It falls out of the timing solution. It has to be, you have to get that precision in order to be able to count every pulse perfectly. And so the whole goal with pulsar physics is to say, given we can get this precision, what kind of question can we ask the pulsar that it's going to allow us to make an amazing answer? So here's a kind of contrived example of that. So this particular pulsar is a canonical millisecond pulsar. It's got a white dwarf in a very circular orbit, just like I showed you. So here is the projected semi-major axis of the orbit. It's about 11.3 light seconds, which is about 3.4 million kilometers. I mentioned that it's very circular. Here's the eccentricity. It's about 1.30 plus or minus 0.04 times 10 to the minus 6. That sounds quite circular, but I don't really think in terms of eccentricity. I don't know how circular that actually is. But you can take an ellipse, and it can have a semi-major and semi-minor axis. And I know the difference between semi-major and semi-minor axis. So given these measurements and their errors, what is the difference between those two? And the answer is 2.8 plus or minus 0.2 millimeters. And this thing is 2 kiloparsecs away. So if you ask the right questions, you can get answers like this out of pulsars. And that's the whole trick. Can you ask the right question that gets you interesting physics? And the people who did this best and first are Joe Taylor and Russell Hulse, as you guys are very well aware of, with the double neutron star system B1913 plus 16. And they used pulsar timing. And they measured, as you know, the relativistic several different relativistic effects in this binary, and showed that the orbit's decaying due to the emission of gravitational waves. And so this was the first indirect detection of gravitational waves. And here are the famous plots that show that. So this is a great example of what you can do with pulsars. And people have continued to do science that's like this since the 70s and 80s. And we have a whole bunch of fantastic systems where we're getting a wide variety of science out. What we would like to do now, though, is do a direct detection of gravitational waves. So that's the question we're mainly going after right now. And so, yes, absolutely. Yep. Yeah. Yep. That's right. Yeah. So, but I can go into it a tiny bit right now. I mean, even with this, with the Hulse-Taylor binary, which is not even a true millisecond pulsar. It's got about a 60 millisecond spin period. Those systems have, we don't understand it at all, some rotational instabilities that are caused by either magnetospheric effects or internal things that are going on inside the neutron star itself. And that leads to a phenomenon known as timing noise. The younger the pulsars, we see a lot of timing noise. The pulsars like the Hulse-Taylor binary, we see less. And we see even less amounts of timing noise in the millisecond pulsars. But no one knew until you have 8, 10, 12, 15 years of very high precision timing data on the millisecond pulsars whether we're going to end up being dominated by timing noise for the millisecond pulsars. And I'll skip to the bottom line. We're not now. We do see timing noise in some of our millisecond pulsars, but they're behaving beautifully. And this is why when the whole gravitational wave detection effort started with pulsars about 10 or 15 years ago, it was people had no idea whether it would even be possible or not because we didn't know if the clocks were going to be good enough on long time scales. And they look great. That's the bottom line. So that's what we're doing. We're using a whole bunch of good millisecond pulsars scattered around the sky, timing them for probably, in truth, decades. We already have about 10 to 15 years of data in the bank for a lot of millisecond pulsars now. And we want to time them at the hundreds of nanoseconds level. And if we do this, we can make a correlated detection of early and late arrival times from these pulsars that are indicative of gravitational waves. Matter of fact, it's the exact type of measurement that LIGO does. We're measuring differences in light travel times due to the stretching and compressing of space-time. And so it really is exactly like the measurement that LIGO makes. And there's three main groups that are doing this now. NanoGrav in North America, the Parkes Pulsar Timing Array in Australia, and the European Pulsar Timing Array in Europe. And I'll talk a little bit about each of these different groups. But the basic way this observation and measurement works is kind of like this. And I'm going to give you a slightly simplified cartoon example, but the gist is exactly correct. So let's say that I'm the Earth, where all of our radio telescopes are, and you guys are all pulsars. So if a very low-frequency gravitational wave passes through the galaxy, it stretches and compresses space-time. You guys are all bobbling on gravitational waves, and the Earth is bobbling on gravitational waves as well. And if the Earth gets bobbled towards you, all of your pulses are a little bit early. All of the pulsars back there, the pulsars are a little bit late. All of the pulsars in these directions are not affected at all by that. So it's basically like that. We see differences in arrival times based on the motion in space-time due to gravitational waves from these various pulsars around the sky. Now, the part that's not quite true about what I just said there is I kind of gave you a dipolar type example. But as you well know, gravitational waves propagate. They're quadrupolar in nature. So it's not a dipolar signal. We see a quadrupolar correlated signal around the sky. But it's exactly the same principle. And we can calculate exactly what the correlation pattern is on the sky. And in general, it's mostly the Earth's term, because the Earth is the common mode signal to all your different pulsars. You guys are all bobbling at your own. That's like a noise term. But the Earth is common to all of you. So we should see a quadrupolar correlated signal from our pulsars due to the motion of the Earth due to gravitational waves. And that's basically the gist. Very low. So we're called NanoGrav because we're looking at nanohertz frequency gravitational waves. So we're using these timing baselines of 10 to 15 years. We're looking for gravitational wave periods of years to decades. So very, very long wavelength gravitational waves. So these are the three groups. This is just a little table that kind of shows you the telescopes and how we kind of compare. We have a big advantage in NanoGrav in that we have the two best pulsar telescopes in the world right now. And that's because of sensitivity. I mentioned these pulsars are very faint. We need huge telescopes. And these are the two biggest and best. As you well know, though, they're under very, very big funding trouble by the NSF. The NSF wants to defund both of these ASAP. And as I'll show you, I think that's would be tragic for our science right now. The other telescopes that are used by other groups are smaller, but they get a lot more telescope time on those smaller facilities. And that extra time that they get helps to balance out some of the sensitivity that they lose, but not all of it. Our data are by far better than those other two experiments right now. And because of that, we are gaining. Our gradient is much steeper. So we're doing better quicker than those other experiments are. But there's a bunch of other disadvantages and advantages to each of these different groups, and I won't go into the details. The important thing is that last year, all three of the groups came out with major new gravitational wave limits, and we're continuing to do good stuff now. So I'll kind of summarize where we are. So the Australian government wants to shut Parkes as well. So the Square Kilometre Array, the Australian government's putting a lot of money into the Square Kilometre Array. Parkes is a 50-plus-year-old telescope. They say, oh, just like what NSF is saying, we need to close these old facilities. But these very sensitive, older single-dish telescopes are basically designed for pulsar work. The newer arrays are not. It's much, much trickier to use these newer arrays for pulsars. So to give you an example of what this was the data release that we in NanoGrav gave out last year. This shows the observation date. So this is back when NanoGrav started, back in about 2005. And you can see each colored point here represents a day at the observatory. The different colors represent different frequencies because we use multiple radio frequencies to remove the interstellar medium effects. And here's all the pulsars that we were timing as of last year. And there's about 42, I think, pulsars there. Some of them, we have incredible amounts of data and multiple frequencies. Some of them we just started just recently. You can see a lot of them we've started over the last few years. And this has been a big goal of ours, is to add more pulsars to the array. And I'll talk about that. But huge numbers of data points. We have many, many hundreds of thousands of arrival time measurements. Here's that same pulsar I showed you before, J1909, the one that had the 100 nanosecond or 200 nanosecond residuals in its discovery plot. When you look at our NanoGrav data, here's the data from the last 10 years. Here was a previous generation instrument. Here's the new generation instrument. You can see the data got better when we turned that instrument on right here. We're getting the RMS timing residual for this pulsar is about 50 nanoseconds over a decade. So this was the point that I was making earlier. We did not know if any pulsars could be timed at 50 nanoseconds RMS over a decade timescales 10 years ago. We had no idea. Yes, and we're in that process right now of triaging some of our pulsars. So there are some pulsars that, because of interstellar medium effects or internal spin effects or magnetospheric effects, that by measuring them, we're seeing red noise processes, and we say, nope, this guy's no good, and we're replacing it with newer and better pulsars that we found. Absolutely. So well, that's a tricky question to answer. So for most pulsars, most of the millisecond pulsars, because they're so faint, the combination, our dominant noise source is just radiometer noise. It's just the noise from the receiver and the fact that the pulsars are so faint. That's the majority of our pulsars. So that's what's causing us to continue to add more pulsars, because we get a kind of like a root N improvement that way. But for the pulsars that's not our limiting factor, sometimes we're starting to see some red noise in some of those systems. That's not due to instrumentation. That's due to a pulsar or interstellar medium effect. So we can kind of separate whether the problem is a sensitivity issue or a pulsar issue. And if it's a pulsar issue, we get rid of the pulsar. Yes. So this is the dispersion measure. So I'm not going to talk about the interstellar medium at all. There's great physics we can get out of the interstellar medium from our measurements, but in general, it's a nuisance parameter if you're going for gravitational waves. But yes, this is the measurement of the dispersion measure, so the column density of electrons between us and the pulsar. And as you see, there's a wiggle, and this wiggle, there is a one-year periodicity in this wiggle. Some of our pulsars show a very strong one-year periodicity. And what that is, it's pretty astonishing. These pulsars are moving on the sky. So we see their proper motion, and there's a gradient of electrons. And if you move on the sky and the Earth's going around the sun, there's a parallax and proper motion effect that you see a helical pattern on the sky. So it's the helical motion on the gradient that causes this periodicity. It's pretty amazing, and we can measure that beautifully. This is just with reference to the average dispersion measure. So that doesn't mean anything right there. So we've removed the average dispersion measure off of that. But this is what a really good pulsar looks like. They're great. We have a whole bunch of pulsars that are better than, say, 300-ish nanoseconds. And most of our pulsars are better than a microsecond RMS over a decade. Yeah? No, not really, because there's a whole bunch of other effects that I mean, in general, you don't get a gradient. It's much more complicated than a gradient. Yeah. I mean, it's informative about the velocity a little bit, and it's slightly informative about the distance, but we have better ways at getting both those things, so it's not that useful. So that's what our data look like. Where do the gravitational waves come from that we're looking for? And in general, our main signal, we think, are the supermassive black hole binaries that are in the centers of other galaxies. And during hierarchical structure formation, as galaxies form and they merge, we think that their black holes in their centers eventually merge as well. And this is potentially detectable from a single source, even with a single pulsar, if we got lucky enough. And so this shows the time delay that you would get for a very massive system, so a reduced mass of about 1 billion solar masses. That's what we're looking at here. We're looking at billion-ish solar mass black holes. And gravitational wave frequencies in the nanohertz regime, or maybe tens of nanohertz. But you can get of order 10 nanosecond residuals. So if we have enough pulsars that we're timing at the tens of nanoseconds significance, we can make a correlated measurement. That's the gist. Observing frequencies? Yes, at least 2, and some of the pulsars we're using 3 or more. And that's to remove these interstellar medium effects. That's crucial. Yeah. So as an example, here's there's a very famous source. It's a radio galaxy with these two jets that appear to be processing. This was published back in the early 2000s. When it was published, the idea was that this system had a 5 times 10 to the 10 solar mass black hole binary with an orbital period of about a year. Now, as an observer, if you ever measure something that's got an orbital period of about a year, you should be a little bit suspicious because there's at least one other thing I can think of that has an orbital period of a year. And it turns out if this thing were real, this would have been the gravitational wave signal that we would have seen in our data already on hand. So this is ridiculously large signal. Obviously, that does not exist. So you can actually rule out certain systems already from our data, or say that general relativity is wrong, which I don't think we want to do that right now. So that's kind of this next point here. So OJ287 is a little bit too far. So that's not quite, we don't have the sensitivity yet to rule that out, as well as some of these other new systems that have been mentioned. This one was just published last year. If this one were a bit closer, we should be able to see this individual signal as well in our data right now, but we can't. But this is a tough, going after these systems in multi-wavelength observations is very, very difficult to try to find them in other ways. So there could be many of the systems that we're missing. But in general, when people have simulated the whole ensemble of supermassive black hole binaries throughout the sky, we would probably have to be lucky to find one, an individual one right now. Only about 10% of the simulated universes would we get a detection of an isolated system first. In general, we're going to see a stochastic background first. That's what most people believe. And so you can actually calculate quite easily what the stochastic background would be from supermassive black hole binaries integrated throughout the universe. And you get a spectral index and an uncertain amplitude range that depends on the merger history of galaxies throughout the universe. But people are working on this. There's a whole bunch of papers. So what we're looking for in general is a correlated signal between pulsars that is a power law as a function of the gravitational wave frequency. That's the general signal we're looking for. And the way that that's measured, the way that correlation is determined is this thing called the Hellings and Downs curve. It's a 2-point correlation function between pairs of our pulsars separated by an angular distribution on the sky. And there's two terms I already mentioned. There's the Earth term and there's the pulsar terms because each side is being jiggled by gravitational waves. There's signal in both, but for right now, because we don't know the precise distances to the pulsars, we can't use that pulsar term. So that's a noise term. And so all these red points, that's the noise term caused by that pulsar term. The average signal of this curve here is due to the Earth's signal, and that's the one that we think we're most likely to be able to measure. The nice thing about this correlation is that it's quadrupolar, right? That's why you get this very specific shape. And it's different for the other types of errors that we're likely to see. Everything is referenced to atomic timescales, for instance. And if our atomic timescales are drifting, all of our pulsars are going to drift in the same way. That's a monopolar type signal. If we have an error in our planetary ephemerides, which we use the JPL planetary ephemerides, if there's an error there, in general, that causes a velocity error in the center, the barycenter of our solar system. That's basically a dipolar type signature. And to give you an example, we're seeing stuff like this in our data now. The best, most accurate JPL ephemerides, our pulsar timing data has just shown that there's an error in JPL's mass and position of Jupiter. And we can see that in our data. The Juno probe just got into orbit around Jupiter, and they're in the process of updating Jupiter's position and mass right now. And that's going to remove this error in our data. So we're actually able to do stuff as well as JPL sending probes to planets. It's kind of astonishing. So what's our results for gravitational waves? So there's several summary papers that came out. In NanoGrav, the paper came out in early this year, and the Parks group, theirs came out last summer. They made a big splash at the time and said that they were ruling out many of the models for the mergers of galaxies as a function of redshift. We think they overstated their claim. So the most optimistic models, where the black holes completely evolve purely due to general relativity and nothing else, and black hole growth is dominated by those mergers, not by accretion. Those are the two key things. Cause optimistic models, such as this band here. This is frequency on the x-axis and gravitational wave amplitude. Here's the band of these optimistic models, and here's the Parkes limit. It's below the band. They should have seen something. Most of the other realistic models have much wider error bars, and the best measurements are within those ranges right now. And then if you add other realistic things, such as you have lots of stars at the center of galaxies, or gas, or add eccentricity to the supermassive black holes, other environmental effects, that can cause turnovers in the spectra so that our noise curves are not seeing something. So if any of these things are in effect, if we're towards the lower end of these error predictions, or if there's any environmental effects, it's reasonable that we would not have seen something yet. But the important thing I think you'll get out of these slides is that we're doing astrophysics now. We're informing models with our data now. They're becoming informative. And I think that's a really exciting time. Like I said, 10 years ago, we had no idea if we'd be able to get this far. So the black curve is just our noise curve. Basically, it's we are most sensitive to the longest. So this is frequency. So low frequency is down here. High frequency is up here. We get more and more sensitive as we go to longer and longer periods or lower frequencies. So it's just like a LIGO noise curve, exactly. This spike is due to the fact that we fit for positions on all the pulsars, so that's a 1-year spike, so we have no sensitivity at 1 year. And in general, we think, whatever, this is the power law that you expect from supermassive black holes. So we normally quote at the lowest point on the noise curve where that power law slope, that's where our limit is, basically. Yep. This is a prediction for the square kilometer array. So this is predicting forward after, I think it's 10 years or 5 years with the square kilometer array, where the sensitivity would be. So very far into the future is what that's a prediction. Yes, I will get to these things. So I should mention, people are still working on the modeling side and using Illustris, the cosmological simulations, using the best known cosmology and hierarchical structure formation and merging scenarios that we know right now. The best models are slightly lower in amplitude than the previous generation of models. And so there's this nice paper that just came out recently. This is quite messy, but here's the limits that came out last year. This dark line right here is the median prediction from these new Illustris simulations, and it's just below the upper limits, which is interesting. So this is probably the best astrophysics that are going into the models, and they're suggesting it's just below where we are right now. So that's interesting. No, so this, I have another slide I didn't leave in. They also use some microphysics about they're assuming gas and stars, and they do get a turnover, just like we showed in the previous diagrams, but the turnover happens above the frequency where the limits are. So the turnovers are happening like in here. So that's good. But the thing is, we don't know the microphysics. The last parsec problem is still a problem, theoretically at least. We don't know exactly what's going on microphysics-wise at the interiors of the galaxy. So we really don't know where or if there is a turnover here. There almost certainly is, but where is it? But the interesting thing is, using the best cosmology simulations now, we're close. So someone asked about combining data. So this slide will go into that a bit. This is showing our predictions for the future. So this slide shows where we are now. So these are the current limits. This is gravitational wave strain versus time. And in using data from the data were from a couple years ago. Here's our limit. Here's the NanoGrav's limit. Here's PPTA's limit. These are the numbers that we have now. These are our predictions of how we're going to improve with time. We had data up to this point when NanoGrav released this limit. So that's where the red line and the black line cross. As we're predicting forward, here's our gradient, an improvement. So by 2018, we should be below the predicted band. And this is the Sassana et al., kind of the most well-respected models of these mergers. Those new measurements, the new models are about right here. They're at about this level using the Illustre simulation. The green curve shows a 50% detection probability. This is basically a 3 sigma detection, and this is a 95% detection probability. Once again, of a 3 sigma detection, 95% of universes that we simulate, there's a detection. And you can see that within the next few years, we exit this band and have a really good chance of detection. The way these bands split is what happens if we lose our telescopes. If we lose Arecibo, we get the high points. If we continue on as normal, we get these midlines. And if we get a whole bunch of extra telescope time, if a benevolent billionaire decides to give us a whole bunch of money and we pay for all the telescope time, we get these more steeper curves here. So this is for NanoGrav alone. So things look optimistic. If we combine the data in the International Pulsar Timing Array, which we're all working on, we get a big benefit as well. We get about a factor of 2 improvement in gravitational wave sensitivity. The problem is there's a bunch of egos in these 3 collaborations. We all want to look at our own data. We all want to make our own limits. We all want to make our own detections. So it's a little bit slower. There's a lot of politics. There's systematics combining very different data sets. We're working on this, but it's slower. But this extra factor of 2 improvement is a very, very big thing, and you'll see 1 or 2 IPTA gravitational wave limits in the next year or 2. In NanoGrav, we're working very hard on the 11-year data release, which is data through the end of 2015. Our data release is almost out, and we have preliminary results. So this is highly preliminary. It's very interesting. So we've increased the number of pulsars by quite a bit. We have twice the number of arrival times, and all of these new data are with our new instruments, which are better. Very interestingly, is our stochastic background limit is about the same, the 95% upper limit, as the 9-year data release. Now, at first, that sounds bad. But that's exactly what you expect to see as you start to approach a detection. And interestingly, these are from MCMC's runs on our data, analysis runs. If you look at the 9-year data set, this is the posterior, this is the predicted band, this is the posterior of what the gravitational wave amplitude was. There was no lower bound. Basically, it could have been 0, and it was consistent with the data. When you add with the 11-year data set, that chops off now. We are seeing a preferred level of a correlated red noise signal in our data. Now, if you compute the Bayes factor of and do a model selection using Bayesian evidence, the Bayes factor for a correlated gravitational wave signal it's a small Bayes factor. It's only about 2 right now. But the beautiful thing about this measurement is there's a gradient. It improves in time. So the next data release we have in another year and a half, hopefully that Bayes factor goes from 2 to 5, or whatever the number happens to be. But it's interesting that right now we see what appears to be correlated red noise in our data. That's very, very interesting. That's exactly what we expect to see. No, that's why the 95% upper limits, if you integrate both of these curves to 95%, you get almost the same exact level, because these tails are that 5% tail. So the upper limit is almost exactly the same. It's just that you shut off all of this lower the lower amplitude probability. But what this means is that actually if this is correct, and if this is due to gravitational waves, which I'm absolutely not claiming, it means that the well-known models that are out there, not even the ones that are ridiculously optimistic, but the well-known models may have something to say about the way black holes are merging throughout the universe. And I think that's very interesting. This is a stochastic background, so it's integrated over hundreds and thousands of sources. So it's the ensemble. They're all purely sinusoidal. That's right, because we're not seeing the mergers. We're seeing when these sources are orbiting on years time scales, And so they don't change very much over the 10-year window of our observations. So we're seeing all those sinusoids added up together. That gives us a power law spectrum. All right.
Would you have expected to see such a big difference by simply going from 38 to 48?
No. So I think most of this improvement comes from the fact that we have, for a lot of these pulsars, we'd had before 9 years of data. Adding 2 more years of data really helps. I can show this a little bit on these noise curves. Yeah, so the way this works, this is frequency. The longer we observe, we push down in this direction because that extends our timing baseline. So we're pushing down this direction, and at the same time, the gravitational wave background we think is improving. So that's why we have every year or two of data we add, we get a big benefit because the background is stronger at those frequencies, and we have a longer data set, which we also get a square root of n effect as well. So there's 3 different effects that improve. We're going to longer observation time, the background is increasing, and the square root of n observations is improving. So it's that extra 2 years that moves everyone down. That's right. Yeah, so yeah, the square root of n thing moves the whole curve down. That's right. But that's the basic reason why it really helps just adding a few more years of data. There's been some anisotropy analyses right now, and it's tricky to say. So some people think that probably our best chance of detection is to see a stochastic background that's anisotropic, because it might be that we're dominated by signals from the nearest, most massive clusters, for instance. Those might have ensembles of black hole binaries which are in our band. So we might see patchy, at very large scales, signals. So we're doing those analyses, but there's many more degrees of freedom in those analyses too, so the limits are not as good. In the last couple of minutes, because I wanted to talk about other physics that we're doing, but I know you guys are interested in this stuff, so I'll go quite quickly. I want to mention how we can do better. Okay, and there's several different ways that we can do better. We're working on improving our instruments. I mentioned Moore's law has been tremendously important for this field. There's only one little bit of instrumentation improvement that we can do, which is using the current telescopes, and that is to build these very broadband receivers. This is the state of the art right now. This is observing frequency. This is where we started at NanoGrav. We had this much bandwidth. Then Moore's law let us get this factor of this order of magnitude improvement. Now we can get another factor of 3 or 4. This helps us remove systematics from the interstellar medium, as well as just collects more signal, so we have better sensitivity. We do not have these things funded right now, but we're trying to put these on each of our telescopes. This will help a lot. The best thing we can do is to find new pulsars. And so every single major radio telescope in the world right now is using big pulsar surveys, looking for new millisecond pulsars. And the main reason for this is that the gravitational wave strain, the minimum gravitational wave strain we're sensitive to, is inversely proportional to the number of pulsars. And you can think of the main reason is because that 2-point correlation function, the number of points on that is the square of the pulsars. So when you integrate that up, it goes as the number of pulsars. That's the 0th order reason for why that is. That's right. Yeah, but that's exactly right. You don't actually have to wait 10 years, though. This is the beauty of this, because there's still correlations. So even if we only add these pulsars for 2 or 3 years, whatever the gravitational wave signal is doing mostly to the Earth right now causes correlations even in that last 2 or 3 years. And that helps to inform and accentuate the correlations we see over much longer time periods as well. So there's been a huge number of simulations that have done that show this is really important, and it's why we're continuing to add many, many more millisecond pulsars. T is time. That's the total overall time baseline. That's right. Yeah. We've been very successful with more pulsars. This is just the number as a function of time. Fermi has really helped. You may have heard about that. Fermi has showed us that all millisecond pulsars are gamma ray emitters. Fermi is showing us where to point our radio telescopes, and we're finding these new systems. And in just the last couple minutes, I'm just going to flip through just to give you an idea of what we have. With Fermi? Not 100%, but because of the fact that this is astonishing to me, I have given whole colloquia on the gamma ray millisecond pulsar stuff. The gamma ray beams and the radio beams seem to be completely untied from each other, so that you can have a very bright gamma ray pulsar and a very faint radio pulsar, and vice versa. They have completely different pulse profiles. They're coming from different parts of the magnetosphere. Anatoly could probably lecture us a lot on this. But we don't understand why they're so uncorrelated, but that's probably the main reason why not all of our known radio pulsars have gamma ray emission, but most of them do. The vast majority do. So these surveys, my main point that I wanted to get out of this last bit is that they're great for helping our gravitational wave stuff, plus we find a whole bunch of really cool pulsars to do other physics. This one popped out. This is the most massive and most precise neutron star now. It's 2.01 solar masses, and further timing has held this up. The two known solar mass neutron stars have revolutionized dense nuclear physics. I mean, they have a gajillion citations. And the reason why they became interesting is because the high precision timing of millisecond pulsars allowed us to measure their masses using Shapiro delay. And they turned out to be interesting for nuclear physics. We're finding tons of these interesting so-called black widow systems. There's a whole bunch of great astrophysics that can come out of these. And there's some hints by Roger Romani and company that these systems, because of their nature of their evolution, could be even more massive. So maybe pulsar masses more than 2 solar masses. And that things get very nonlinear for neutron star physics above 2 solar masses. That would be interesting. We're finding evidence of triple systems. I'm going to skip over this. We actually found a triple system. Hopefully some of you, I know Roman knows about this. He wrote a paper on it. There's an amazing system that we found a couple years, 3 or 4 years ago now, where there's a very high precision millisecond pulsar. It's a NanoGrav quality MSP. It's a 100 nanosecond pulsar in orbit with 2 white dwarfs. In a hierarchical system, the inner white dwarf and the millisecond pulsar is here. They're orbiting the center of mass here, and there's an outer white dwarf here. These 2 white dwarfs have different masses, and we have this incredible timing precision from Arecibo. This shows some of the data from the discovery. This is the pulse delay, and it's really just a light travel time delay. As the pulsar moves in its orbit, when it gets closer to you, there's less delay. When it moves further away, there's more delay. That's how we measure the orbits. Here's the outer orbit in the data. This is about a 327-day period. All these dotted points here are our data points. And if you zoom in here, that's this bottom part. And here's, you can see the 1.6-day inner orbit on top of that. There's tens of thousands of data points here. And our error bars on the data points are 1,000,000 times too small to see at this scale. But the Threebody effects, we have 3 point masses. The Threebody effects are exquisite. Let us completely solve the system. We see special relativity plus Newtonian gravity. That's it. And we have incredible precision on the masses. And we're going to have this incredible test of the strong equivalence principle, which I'll spend my last 2 minutes on. Basically, the way this works is that we have, that's weak equivalence principle. I'll leave this up. So the gist is that you have a neutron star with strong gravity, so it has gravitational binding energy, lots of gravitational binding energy, and a white dwarf, which has way less gravitational binding energy. They're orbiting each other, but they are both falling in the potential of the outer white dwarf. It's exactly like the hammer and feather experiment, except for one of the objects has got strong gravity. It's got 10% of its mass energy is in terms of gravitational binding energy. That lets you test the strong equivalence principle, which I won't go into, but by far better than anything else, way better than we think, about a factor of 100 better than lunar laser ranging, which is currently the best upper limits on this. I won't go into it. Don't ask me any questions about this because I don't understand the details of this slide, but some of you in the audience probably will like this. This is a prediction of how the triple system will affect tensor scalar theories with the alpha and beta coupling parameters. And all of the current pulsars and strong equivalence principle tests, lunar laser ranging, and even the best predictions of what Cassini's total data set and Gaia's total data set will do, the triple system blows them all out of the water constraining what the values of alpha and beta, these coupling constants, are for tensor scalar theories. And this system, we just find these because there's still thousands of millisecond pulsars to find in the galaxy because we're sensitivity limited, and we're looking for these to do gravitational wave science. But we find cool other things like this on the way. Yeah, I said don't ask me any questions about that slide. So what about the future? I just mentioned there's thousands of pulsars, tens of thousands of pulsars to be found in the galaxy. We're sensitivity limited. That means we need big telescopes. That means we don't want to get rid of our big telescopes we have now, especially since we think we're seeing potentially gravitational waves, the hints of them in our data right now. But the big gist in the future, there's big telescopes being built around the world, Meerkat and FAST. This is an amazing picture. In China, the 500-meter spherical telescope, it's now fully, well, I shouldn't say it's fully complete. It's fully constructed. There's a lot of work left to be done, but this is 500 meters. That hole in the center is this. These are people in that little hole. That is a huge, huge telescope. But these collecting areas, one of FAST's main science goals is pulsars and gravitational waves. And then the big end state is in sometime 10 to 20-ish years from now is the square kilometre array. And that incredible collecting area will allow you to do tremendous pulsar searches to find most of the pulsars in the galaxy, and then do all the types of physics and gravitational wave studies that I've been talking about using those pulsars. So the SK is really where we want to be internationally, but I think in the US, it would be tragic if we lost Arecibo or the GBT. And I should mention that for NanoGrav, half of our sensitivity comes from the GBT, half of it comes from Arecibo. And it's a real easy way to explain why that is. Pulsars are distributed all over the sky because we're seeing close by ones. Arecibo can only see a small chunk of the sky, but Arecibo is so sensitive. For the pulsars that it can see, it wins, but it's only a small chunk of the sky. All the rest of the sky, the GBT is by far the most sensitive. So for all those pulsars, it wins. And so because of that, it works out that about half of our sensitivity is with Arecibo and half is with GBT. So my summary is basically, I think we have a really good chance in the next few years of making a direct detection of gravitational waves. And on the way, we're going to do a whole bunch of other great physics as well. But we need these really big telescopes because these things are very, very faint objects. Thanks.